Welcome to General Chemistry Mini Lecture Series, Lecture 39, Periodic Properties. You already saw this periodic trend slide in Lecture 8. There we talk about 5 different periodic trends: metallic character, atomic radius, ionization energy, negative electron affinity, and electronegativity. Now we add effective nuclear charge to this slide. We just learned effective nuclear charge from Lecture 38. We know ZEF can be calculated using the atomic number subtracted by the number of core electrons. And we also know that the trend for increasing effective nuclear charge is from left to right, as well as from bottom to top. The trend for effective nuclear charge is the same as electron affinity, electron negativity, and ionization energy. So that's the same trend. All of those 4 periodic properties, they follow the same trend, increasing from left to right, from bottom to top. The electron affinity is actually the energy change when atom gains an electron. For example, chlorine atom gains 1 electron, forming chloride, then energy is released, or electron affinity energy is released. That's why it's exothermic. That's why in some textbook you will see the term negative electron affinity. The word negative simply means the energy associated with electron affinity is exothermic. Electronegativity, En, that's a measure of how strongly atoms attract bonding electrons to themselves. Fluorine has the highest electronegativity with an electronegativity value of 4. For example, in HF molecule, the 2 bonding electrons, they are pulled much closer to fluorine. As a result of that, fluorine end of the HF molecule is partially negative, and the hydrogen end is partially positive. And you can also use those arrow notation to show that the hydrogen end is partially positive and the fluorine end is partially negative. Ionization energy, that's energy required to remove an electron from gaseous atom or ion. What shows here is the first ionization energy. I will go over a little bit more about the other ionization energies in short moment. Now let's look at the opposite trend: metallic character as well as atomic and ionic radius. They increase from right to left, from top to bottom. First, let's take a closer look at metallic character. For metals, so they are malleable and ductile, shiny, so reflect light, conduct electricity and heat, and most of our metal oxides, they are basic and they are ionic. Metals form cations when dissolved in solution, and they lose electrons in oxidation reduction reactions or in redox reactions. So therefore, metals are oxidized. And those are the nonmetals. Of course, nonmetals behave oppositely. For example, while metals are malleable and ductile, the nonmetals are brittle if in solid state. Metals are oxidized, nonmetals are reduced, so they gain electrons. Now let's go over the radii of atoms and ions. Please note, please pay attention here, cations are smaller than their corresponding atoms. For example, you see the ones on the right-hand side, those are the ions. And the larger ones on the left-hand side, the gray ones, they are actually the corresponding atoms. Cations are always smaller than their atoms. For example, lithium plus is smaller than lithium atom. Anions, on the other hand, they are larger than their corresponding atoms. For example, oxide is larger than oxygen atom. So on the right-hand side, that's the anions. So they gain more electrons. That's why actually they occupy greater space. And that made them larger than their corresponding atoms. Now let's take a much closer look at atomic radius. There are several types of atomic radius. First one, van der Waals radius. That's actually also non-bonding atomic radius, which means there is no chemical bond involved in van der Waals radius. That's typically is 1/2 of the internuclear separation of two non-bonded atoms, like in this xenon solid. Next, covalent radius for diatomic molecules and metallic crystals. Please understand those are bonding atomic radius. Let's take a look at chlorine molecule, Cl2. Chlorine covalent radius, that should be 1/2 of the distance between the two identical bonded nuclei. 198, 1/2 of that, 99 picometers. That is the covalent radius for chlorine molecule, Cl2. However, the van der Waals radius for chlorine is much larger. In chlorine molecule, those two atoms, they kind of squeeze together, not those isolated atoms like in non-bonding atomic solids. That's why the van der Waals radius is much longer than the covalent radius. Now, covalent radius for covalent molecules with different elements, not the same element anymore. The covalent radius for hydrogen, that's a length between hydrogen nucleus to the border between hydrogen and fluorine. The bond length is 92 picometers, but the bond length is the sum of hydrogen's covalent radius plus fluorine's covalent radius. Since they are not identical atoms, like here in the Cl2 molecule, the smaller atom should have shorter covalent radius. That's why hydrogen covalent radius in HF molecule, that's 33 picometers, while the covalent radius for fluorine in HF molecule is 59 picometers. 33 plus 59 equals 92 picometers. The metallic radius is 1/2 of the distance between two atoms in a metallic crystal. For example, sodium, the metallic radius is 186 picometers. Now let's take a look at ionic radius. It is determined by the distance between two ions that are barely touching each other. Like in sodium chloride, the bond length should be the sum of sodium ions radius plus chloride radius. So sodium ion radius in sodium chloride is 102 picometers. Chloride radius in sodium chloride is 181 picometers. So those are the ionic radius. But now let's look at sodium's metallic radius, 186. Therefore, the ionic radius is much smaller than the metallic radius. Sodium's van der Waals radius is even longer because it's a non-bonding. Let's do the same for chloride. Chloride radius is 181 picometers, but chlorine atom covalent radius is much shorter. However, the van der Waals radius is longer. Therefore, when you answer questions regarding radius, you need to make sure what kind of radius are we talking about. Are we talking about ionic radius? Are we talking about metallic radius? Or are we talking about van der Waals radius? They are very different. We just learned from lecture 38 the effective nuclear charge increases from left to right. An increasing effective nuclear charge means that there is a stronger attraction between the nucleus and the valence electrons. That attraction makes the atomic radii much, much smaller. So therefore, the atomic radius, the trend, is the opposite. That's why the atomic radius increases from right to left. When we move from top to bottom, atomic radius increases because of the additional periods. Now let's rank the following atoms in order of increasing size. We have these 5 atoms. So first, let's locate those 5 atoms in the periodic table. Here is sodium, magnesium, silicon, chlorine, and fluorine. Let's use this arrow diagram. We know going this way from right to left, the atomic radius increases. What does it mean? It means sodium is larger than magnesium, and magnesium is larger than silicon. Silicon is larger than chlorine. So we use this trend in answer this part of the question. Now let's compare fluorine and chlorine. The radius increases from top to bottom. So what does it mean? Comparing fluorine size with chlorine, which one is smaller? Fluorine is smaller. So therefore, fluorine should be the smallest. Now we easily solved this problem using this arrow diagram. Very similar to this, you should be able to predict other periodic properties. You just need to remember the trend. For atomic radii and metallic character, they go with this trend. And for effective nuclear charge, electron negativity, electron affinity, and ionization, they have the opposite trend. Doesn't matter which trend it is, but if you follow the same strategy, you should be able to answer those questions correctly. Now let's rank each side of the ions in order of increasing size. The first one, they are all 2+ ions, which means they are all in group 2A. So therefore, if in group 2A, so we just use this trend, that's increase that way. Calcium is here, barium is here, magnesium is here. So therefore, which one is the largest? Barium 2+. Which one is the smallest among those three? Magnesium 2+. If you take a closer look at B, you will realize that they are isoelectronic. In other words, this is an isoelectronic series. For isoelectronic series, whichever has the largest effective nuclear charge should have the smallest size. Among these isoelectronic series, calcium 2+ has the largest ZeF, therefore it should be the smallest. On the other side, sulfide has the smallest ZeF, then it should have the largest size. So therefore, once you find out the order of those 5 species in ZeF, then the opposite order should be the trend of size. Now, iron 2+ and iron 3+. For cations formed from the same element, you see both are formed from iron. The higher the positive charge, the smaller the ion. That's why iron 3 is smaller than iron 2. This table shows the successive ionization energies. A while ago, I already showed you the first ionization energy. That's the energy to remove an electron from the neutral atom. Then the second ionization energy is actually the energy required to remove an electron from the 1+ ion, and so on and so forth. Okay? Removal of each successive electron costs more energy. That's obvious. After electrons are removed, those ions would have more photons than electrons. Thus, outer electrons are more attracted to the nucleus, which means it becomes harder and harder to remove additional electrons. That's why you see increase successive ionization energies. We notice regular increases in energy for each successive valence electron. For example, aluminum, that's a group 3A, 3 valence electrons. Therefore, all of those 3 electrons removed their valence electrons. And the increase in energy is kind of regular. What does it mean? This first one, the first ionization is about 600, second ionization about 3 times more, and then the third ionization is less than doubled. However, the fourth ionization energy for aluminum, that's actually the removal of the first core electron. This one is not valence electron anymore for aluminum. And look at the energy increase from the third ionization energy to the fourth. How many times? That's about quadrupled. And here, that's triple. Here you see it's less than double, and here is quadruple. So therefore, it's a much larger increase in energy when start removing core electrons. That's it for lecture 39. If you like this video, please subscribe this channel and recommend those videos to your friends. I will see you guys in lecture 40, chemical bonding models.